On a gray morning in late 1943, a U.S. Navy salvage crew eased a captured Japanese submarine onto the deck of a high-capacity transport moored in a sheltered bay. The vessel had been taken after a brief encounter in contested waters. She was neither pristine nor fully destroyed, but she arrived with enough systems intact that Navy mechanics believed they could restore basic power and examine her machinery under controlled conditions. The craft's silhouette was unmistakable to those who had read intelligence reports. A low freeboard, a compact conning tower with narrow optics, and hull lines that betrayed careful hydrodynamic shaping. The men who boarded her did not expect novelty. Submarines were machines of familiar parts: diesel engines, batteries, ballast tanks and valves, electric motors, compressed air manifolds. What they did expect was the usual wartime improvisation: missing gauges, scoured instruments, scorched wiring. What they did not expect, and what would fix their attention for months, was a deliberately hidden system whose logic and construction spoke to the Imperial Japanese Navy's doctrine of denial by destruction. The initial phase of the operation was practical. Mechanics cleared tense areas, established gangways, and neutralized obvious hazards. Live torpedo warheads were removed under ordnance supervision. Compressed air reservoirs vented and fuel lines drained. Once the immediate dangers were isolated, engineering petty officers moved into the forward compartments to assess the electrical system and the battery banks. The submarine's battery compartment had been flooded in the skirmish, but many of the lead-acid cells were corroded rather than ruptured. Wires that connected those cells to the main switchboard still bore stamped markings in Japanese script. Insulation had been chafed but not entirely severed. Naval electricians brought portable charging rigs and, under careful supervision, applied low-level charging currents to revive several cells, just enough to light patched instruments and allow gauge readings. That limited restoration of power enabled a more detailed inspection of the submarine's internal systems without resorting immediately to destructive disassembly. Methodical inspection revealed a pattern. Circuits and cable runs had been dressed with unusual care in critical zones. Wiring that led aft toward the torpedo room and the after bulkhead was bundled into armored conduits and terminated at junction boxes that were not standard for Japanese yard practice, boxes with additional sealing, rings and secondary locking plates. Under one access panel, a maintenance chief found a small, purpose-built detonator magazine stowed within a toolbox cavity. Its clamps looped through a leather strap and then lashed to the hull with a length of wire. The magazine was empty. The detonator carriers bore signs of prior insertion. Nearby, in a false compartment behind a bulkhead panel, technicians discovered a coiled length of heavy-gauge cable that ran into the keel and then upward to a panel behind the officer's berth. At first glance, the arrangement looked like redundant battery wiring. On closer analysis, it became clear that the cables formed part of a discrete, isolated system intended for an entirely different function, one of denial rather than propulsion. The term the Americans would use in later reports, self-destruct mechanism, was not a phrase found in Japanese engineering drawings. The system's components were pragmatic and blended into existing ship architecture so thoroughly that only a careful examiner could detect their integration. The wiring entered the detonator magazine through bulkhead glands identical to those used for lighting circuits, and the heavy cables were routed with the attention paid to salt spray protection, heat shielding near engine spaces, and vibration dampening. The entire assembly suggested premeditated concealment. It would be simple to rig and equally simple to activate in the event of imminent capture, but it would not be visible in cursory inspections or to boarding parties looking only for ordnance. Once these discoveries were recorded, bomb disposal and ordnance officers were summoned to render the system safe and to examine the type of demolition components the Japanese had chosen. Their analysis respected a cardinal rule of post-capture procedure: preserve evidence. Where possible, charges were left in place and examined in situ rather than removed. The ordnance specialists worked with petroleum ether, insulated tools, and layered shrouds to move components for laboratory analysis on the ship. Their preliminary reports emphasized what the system was designed to achieve: rapid, reliable wrecking of vital systems and destruction of secret equipment and documents, executed with minimal preparation, and by means that would not require prolonged exposure of crew to enemy action. The constraints of the mechanism, compactness, concealment, immunity to inadvertent activation, were clear. Technicians documented several distinct features. First, explosive charges, small concentrically wrapped cylinders, had been placed adjacent to keystone elements, the gyro stabilizer in the navigation locker, the radio transmitter rack battery terminals, and the torpedo exploder gear. These charges were not the massed demolition blocks that an aerial scuttling would use. Instead, they were surgical, each positioned to disable a system quickly without necessarily detonating the hull. Second, the detonation chain was arranged with redundancy. Multiple parallel runs of heavy-gauge insulated cable converged at one central switchboard, then diverged to individual charges through series resistors and detection circuits. Third, and most notable, the initiation method combined several activation modalities: manual initiation from a concealed hatch, a remote electrical firing circuit accessible from the conning tower, and an autonomous seawater-triggered contingency that would become of major analytical interest to Allied engineers. The manual initiation was straightforward in concept: a guarded switch located behind the captain's sleeping area and masked by a false panel. The switch itself was heavily booted with corrosion-resistant seals and an intentional detent to prevent accidental flipping. It connected to the central firing bus through a high-current relay system designed to trigger instantaneous firing when the circuit was completed. The remote electrical firing circuit presented a different engineering pattern. From the conning tower, a small, nominally innocuous-looking toggle, labeled in Japanese, connected to a membrane-sealed cable leading through the conning tower collar. That cable entered the control housing where a rotating cam assembly, dependent on the compressed air manifold, could be adjusted to delay or sequence charges. The design showed a sophisticated understanding of field conditions. By allowing initiation both from inside the watchroom and remotely from the hatch, a single officer could set the system as he abandoned ship, or a watchstander could initiate it if capture seemed imminent. But the most technically arresting element was the seawater-triggered contingency. The Americans had known that many navies employed scuttling valves and charge arrangements that would be actuated by flooding or by pressure differentials. What they found here was a compact electrochemical initiation system that used the onset of seawater ingress as an intended trigger. In one intake's manifold, engineers found an assembly resembling a saltwater sensor, two closely spaced, normally insulated plates connected to a bridge circuit. When exposed to salt water, the conductivity between the plates increased, closing a latch in the firing relay and sending a predetermined pulse down the heavy cable to initiate selected charges. It was a design that offered automatic activation in the case of catastrophic hull breach, and its deliberate placement near compartments that would flood first showed tactical forethought. All of these components raised important technical and legal questions for the U.S. Navy. Were these systems intended primarily to deny materiel and intelligence to the enemy, or were they also meant to endanger boarding parties and rescuers? The ordnance officer's conclusion, carefully worded, was that the charges and their protective shrouds were arranged to direct blast and fragmentation inward, toward equipment rather than outward into water channels. That suggested the primary aim was to render the boat unusable, destroy cryptographic secrets and radio equipment, and make salvage operations time-consuming and hazardous, not to inflict mass casualties on boarding crews. The careful seals, clear initiation redundancy, and local placement of charges supported that interpretation. The designers prioritized denial of intelligence and systems rather than casualty maximization. Detailed forensic analysis of the firing circuitry followed. Electricians traced cable runs, measured insulation thickness, and drilled into insulation sheaths to sample lead compositions and cloth braiding. They found a mixture of domestic copper conductors with a protective coating historically used by Japanese naval yards, an enamel derived from resin compounds that resisted salt spray. The relay assemblies used porcelain insulators and mica-based capacitors, and contact points were alloyed with a small percentage of silver to reduce arcing at high current. Such details indicated an intent to ensure reliability even after seawater spray and mechanical shock. The capacitors themselves had been placed behind fireproof bulkheads. They contained modest energy storage, enough to ensure decisive initiation when combined with battery backup. Chemical analysis of the demolition charges revealed composition consistent with wartime. Japanese naval demolition ordnance A cast explosive charge bound within a thin brass tube, with a shaped hearth liner in a few instances intended to focus blast energy into gear housings. The explosive fill was identified as a composite naval explosive used by the IJN, one whose exact name and formula were recorded in classified ordnance circulars. In vernacular reports, the Allies simply referred to it as Japanese Naval Demolition Compound. Whatever its exact composition, its performance characteristics were adequate for the designer's intent: disable delicate mechanical and electrical systems and render bulky equipment unsalvageable without a full-scale demolition procedure. Returning to the battery banks, mechanics discovered that the self-destruct bus was tied into the negative terminal network at several points. The buses employed fuse blocks designed to blow under sudden overcurrent, preventing false initiation and making unanticipated bridging less likely. Nonetheless, the existence of fusible elements suggested that the system designers knew that an electrical connection could be lost in shock. They therefore provided a dual-channel initiation, a primary electric firing circuit, and a parallel seawater sensing path. This redundancy reduced the odds that a boarding party could thwart the self-destruct simply by severing wires. It was a small, deliberate engineering choice with large tactical consequences. The salvage crew proceeded to create controlled tests. In a remote portion of the yard, far from populated facilities, ordnance technicians reconstructed small sections of the system for inert trials. They wired mock detonators, non-explosive analogs, into replica circuits and subjected them to seawater immersion, voltage surges, and mechanical shock to observe behavior. Those tests, performed under strict range control and recording equipment, confirmed what the initial observations suggested. When seawater bridged the sensor plates, the bridge circuit produced a reliable signal that passed the firing relay and activated the downstream initiators. The tests also showed that deliberate disconnection of the control bus at its bridge point prevented activation, but only at the cost of full access to the wiring looms and junction boxes, work that required time and exposed technicians to risk. The intelligence implications were immediate. Cryptographers and signals analysts were invited to the dock to examine radio racks and storage lockers, where code books and cipher disks had been stowed. The demolition charges nearest those compartments had been placed to crater the racks rather than to break the hull, a purposeful approach to destroying the most sensitive items while preserving the hull's external integrity. The Japanese had understood the value of intelligence denial. In theaters where capture risk was high, they preferred localized destruction that rendered documents unintelligible without necessarily sinking the boat outright. For the Americans, this meant that rapid boarding operations would always face the possibility that critical intelligence had been neutralized before capture, unless personnel could access and isolate the devices in seconds. Over the ensuing weeks, Navy workshops reconstructed procedural diagrams from the wiring and relay placements. The schematic that emerged was an exercise in defensive simplicity: a central firing bus fed by two upstream power sources, batteries and capacitor bank, feeding individual firing lines that each included arming resistors, fuses, and initiation leads. Control inputs could be manually made at more than one station. The seawater sensors were set to arm only when interior flood levels passed a defined threshold, and mechanical interlocks prevented accidental arming from vibration or pressure changes. The system's designers had made trade-offs. They accepted the risk of a complex circuit in exchange for a high probability that the system could not be defeated easily in the confused moments of boarding or salvage. The mechanics' reports to naval intelligence were precise, technical, and devoid of anecdote. They cataloged dimensions, wire gauges, capacitor ratings, contactor types, and fusible element specifications. The intelligence staff consolidated these findings into formal technical intelligence bulletins that were distributed to salvage commands operating throughout the Pacific. Those bulletins advised boarding teams on the likely locations of initiation controls, the presence of seawater sensors in intake manifolds, and the expected patterns of demolition charges adjacent to cryptographic and communication equipment. The guidance allowed boarding parties to adapt procedures: rapid isolation of the main firing bus, securing of battery banks, and immediate exposure of likely initiation panels. Those adjustments saved time but not all victories. On several occasions in subsequent operations, boarding parties found shelves of charred radio components and half-melted cipher materials, the product of precisely placed demolition charges that had been actuated before departure. The Japanese system had been effective at its intended mission: denial. Still, the knowledge the Americans gained from the disassembled submarine allowed them to reverse many of the designer's advantages. By knowing where charges were most likely to be placed and how circuitry was routed, salvage teams could isolate and remove initiators before detonation in a significant number of cases. The balance between design intent and countermeasures then became a technical contest. A small war of engineering ingenuity played out in shipyards and on quaysides. Beyond immediate tactical consequences, the examination of the self-destruct system yielded longer-term engineering insights. Naval architects studied the structural impact of small internal charges on hull integrity and realized that properly placed internal blast could disable complex machinery while leaving the pressure hull structurally recoverable. That observation informed Allied scuttling doctrine for forward-deployed enemy vessels and influenced the design of protective casings for intelligence equipment. The Allies began to emphasize compact, quickly removable cipher containers and remote kill switch overrides for their own systems. Material science benefited as well. Tests of detonator magazine construction, brass carriers, insulated pins, and explosive cups showed how Japanese yards balanced corrosion resistance with manufacturability. The Allies incorporated some lessons into their own magazine designs, preferring certain brass alloys and dielectric inserts that resisted seawater creep and handled mechanical shock. Likewise, the use of mica capacitors and silver alloy contacts in relay assemblies prompted reconsideration of contact metallurgy in high-current naval circuits. Although Allied supply lines were abundant, the wartime lessons of economy and redundancy, learned from a captured foe, were useful in designing systems that were both reliable and reparable under combat stress. The months of study culminated in a classified manual that described, with engineering drawings and photographs, the architecture of Japanese submarine self-destruct systems. The manual did not celebrate the device. It treated it as an engineering artifact to be understood, cataloged, and countered. The language was deliberately neutral. The system employs multiple initiation modes to include manual electrical initiation, remote bridge initiation, and automatic saltwater sensing circuits. Charges are placed adjacent to high-value equipment and arranged to direct destructive energy inward. Redundant initiation paths and routing through armored conduit are present to hinder battlefield neutralization. The manual's conclusions emphasized that the primary operational choice faced by the designer was one of denial without unnecessary loss of hull, a theme repeated in several subsequent technical evaluations. As the war progressed and more captured subs were examined, patterns consolidated. Smaller coastal types favored simpler scuttling charges with manual plunger triggers, while larger ocean-going classes used more elaborate systems with multi-point sensors and delayed sequencing. Variants were adapted to theater. In northern operations, saltwater sensing circuits were adjusted to account for ice salinity and low temperatures, while in tropical zones humidity sealing methods were modified to reduce corrosion. These details showed an engineering culture that adapted its denial systems to the operational environment rather than applying a one-size-fits-all solution. By the end of the studies, the empirical arc was clear. What had initially looked like an exotic concealed danger resolved into a logical, disciplined engineering response to a strategic problem. How to ensure that, when a vessel could not be retained, its secrets would not be recovered by the enemy. The Japanese solution, compact charges, redundant initiation, seawater sensing, and careful concealment, was effective, rational, and tailored to the constraints of submarine architecture. The Americans learned to neutralize it by focusing on early isolation of power sources, rapid identification of likely initiation panels, and procedural safeguards during boarding. In that exchange of measures and countermeasures, both sides advanced naval engineering knowledge that would carry into peacetime design and doctrine.